All right, today we're going to talk about diagonalization, and diagonalization is a useful technique. Um, it's one of those things where do you have to diagonalize a matrix? No, but there are some benefits to it, especially if you're dealing with very what's the best way to put it? If you're dealing with high level matrices or higher dimension matrices and you're having to do multiple computations on the same matrix, diagonalization is a very useful tool. So, just to review. So, eigenvector, remember an eigenvector is any vector such that when you do a matrix times, keyword a square matrix, let me be very specific, times a vector, it's the same thing as if you had multiplied that vector by some scalar. So sometimes you might multiply a matrix, let's just use an easy vector like 1, 1. So if I do like a times 1, 1, and then I get -4, -4, then that's an example of an eigenvector because it's the same thing as if I had just multiplied the original vector by -4. Now, not all eigenvectors are going to be as simple as that. And remember, an eigenvector has a corresponding eigenvalue. So, in my example, 1, 1 is the eigenvector with the corresponding eigenvalue of -4. So, the eigenvalue is what makes this matrix equation true. The eigenspace associated with an eigenvalue lambda. Now remember this is one thing to keep in mind. Every eigenvalue has its own eigenspace. And unlike the null space, which is all the vectors that cause it to be 0, remember we do kind of use that idea because what this ends up being is eventually we need the determinant of a minus lambda I, and we set that equal to 0. And we try and find all the vectors that make AU equal to lambda U, because that's the same thing as trying to find A minus lambda I times, let me write it on the other side so it doesn't cramp up this one. So A minus lambda I times U equals 0. So basically, you're looking for U is going to be in null A minus lambda I, because you're looking for the vectors that make it equal to 0. So that's the same as the null space. But notice the lambda in there. You'll have a unique null space for each lambda. So you don't get, like, let's say there were 2 eigenvalues, and each one had 1 eigenvector. When you do that and go through and find it, you don't put the 2 vectors together and say this is the basis of the eigenspace. The basis of the eigenspace is unique to each eigenvalue. So you say this is the eigenspace for lambda 1. This is the eigenspace for lambda 2. Don't just shove both vectors together and say this is the eigenspace for the whole thing. And again, the eigenspace, it's like I knew what I was going to say. The eigenspace is associated. And remember, the geometric multiplicity is the dimension of the eigenspace, which is the same as the nullity of the eigenspace. Geometric multiplicity will be less than or equal to the algebraic multiplicity. And remember, algebraic multiplicity is how many times is an eigenvalue repeated. So that's one thing to be careful of. You can have an eigenvalue with an algebraic multiplicity of 3, but a geometric multiplicity, or the geometric multiplicity, can be no more than 3. And so the eigenbasis, like any other basis, are what are the basis vectors of an eigenspace. So pretty straightforward. Eigenbasis is just what's the basis for the eigenspace. Now, similar and diagonal matrices. So pretty much for all of this, because we're going to have to deal with eigenvalues and matrix inverses, we're pretty much just going to be assuming that every matrix is going to be square. That's just the way it's going to be. Because you can't find eigenvalues or inverses of non-square matrices. So a matrix is diagonal if all of its off-diagonal entries are 0. Pretty straightforward. This is a diagonal matrix. So this is entry 1, 1, 2, 2, and 3, 3. Everything along the diagonal, and technically even the 0 matrix, in all technicality, is a diagonal matrix because everything off the diagonal is 0. Everything's 0, but that's just overkill for a diagonal matrix. This is not diagonal, so again, you look outside of your diagonal entries. And you try not to chop off the decimal point. So, diagonal matrix is going to come in handy here in a moment. Now, two matrices A and B are similar if there's a matrix P such that A equals P times B times P inverse. Now, the other way that you can think about this is equivalent to, think about if you do right multiplication of P on both sides. A times P is equal to P times B. So one matrix times this matrix P on the left is equal to one matrix P or one matrix B being multiplied to P on the right. So if you try and think about it that way, it makes it seem a little bit less arbitrary, because it's kind of trying to find two matrices that when you do a left multiplication for one and a right multiplication for the other to the same matrix, you get the same result. The reason we do the A equals PB, P inverse, you'll see in a moment. Well, I don't know necessarily a moment, but you will see. So we'll take that idea of similarity and we'll combine it with a diagonal matrix. So two matrices are similar. Again, you could do it like this, that AP equals D, or PD, sorry. So what we want to do with the diagonal matrices there is, if I can find this diagonal matrix, my life's going to become a lot easier. Especially, like I said, for larger computations, because it's going to take a lot of matrix multiplication out of this. So this is why it's really important that you want to be able to reduce something into a diagonal matrix. Because if you multiply two diagonal matrices together, specifically, and this is going to be the key thing that you're typically want to go to with these, you want to raise a matrix to a certain power, which means if you raise it to the third power, you're doing the matrix A times matrix A times matrix A. That is quite a lot of computations to go through. But notice, if you're in a diagonal system, then when I multiply row 1 by column 1, well, that's 5 times 5, which is 25. The rest are 0 times 0. But then notice everything else, so row 1 times column row 1 times column 2, that's all zeros. Row 1 times column 3, that's all zeros. Row 2 times column 1, all zeros. -1 times -1, +1, and you kind of get the idea. This would be 0.25. And so why does this work? Because what's happening is the way you set up the diagonal, the only time you ever get two things that are both non-zero to multiply is if they're along the main diagonal, just based on the way matrix multiplication works. So if you were to try and set up all of these matrices together, what ends up happening is instead of having to multiply the matrix A 5 times, all you have to do is raise everything along the diagonal to the 5th power, which is a lot easier than having to do 5 3x3s multiplied all together. This is why you want to be able to diagonalize a matrix, because if you can turn it into a diagonal, then all of a sudden it's a whole lot less multiplication to go about. So let's say a squared, or a is similar to the diagonal matrix D, which means that that property a equals PD P inverse holds. Well, what if you want to square a? Well, that's the same as multiplying those two together. P inverse times P, they cancel each other out, leave you in identity matrix, but then that leaves you D times D, which gets you D squared. A cubed, once again, P inverse and P cancel each other out. And you can see just in general, what's always going to happen is if you need to raise a to the power k, if you know the similar matrix to it, then it's simply just P times D to the power of k times P inverse. And as we showed for a squared, if a matrix is diagonal, it's very easy to calculate. And so you only have to raise this power, raise the diagonal components to a power k times, then you can just multiply P times whatever D to the k came out to be, and then multiply that by P inverse, or you can do D to the k times P inverse and then multiply P, whichever ends up being easier. So part of the benefit of diagonalization, or knowing that two matrices are similar and one is similar to a diagonal matrix, is you can cut down on computations. So earlier on in the course we did some of those, I don't know the best way to call them. It's kind of like traveling equations, but not necessarily. It's so like for this problem, so let P to the k, or P sub k, be how many people are in the city and in the country after k years, just referring to like what area they live in. So typically, like this would, like, you hope that the city has more than 180 people. But initially what you have is there's 180 people in the city, and then there's 30 in the country. So keep in mind, you might measure this in thousands or something like that. So it might be 180,000 versus 30,000. But you can just do that scaling factor afterwards. The smaller you can keep numbers, the better. So if you can say this is in thousands or in millions, that makes computations a lot less likely to, well, not necessarily a lot less likely to, but you're less prone to an error or the machine taking up too much time while doing calculations, because you could have just left it as 10 instead of 10 million. And as long as you had all those scale factors correct, you could just multiply everything at the end versus continuously having to multiply millions when it could have just been multiplying tens or something like that. So this is the transition matrix. That was the word I was looking for. It was on screen too. Good job, me. So basically what it says is this is the amount of people that will stay in the city, and this is the amount of people from the country. So, because notice if I multiply up here, so we'll do the first one. We won't calculate it. So 0.98, 0.02, 0.05, 0.95 times 180 times 30. And so this is the population in each after 1 year. And the way you get that is, so first row, so 0.98 times 180. So that means 98% of the population is staying. Plus, there's 5%, so the 0.05 of the country population that's leaving. And then similarly, that means there's 0.02 of the 180 that are leaving and going to the country, plus the 0.95 of that 30 that are staying. So then you would get city population for year 1, and then the country population for year 1. And eventually what happens is you hit kind of an equilibrium where after a while, because of the amount of people that have left and come back and left and come back, it's kind of like the proportion is always the same. So you have two people that's like, you would end up maybe down the road with like, it's 100 in the city and then 110, or actually that wouldn't make as much sense because more people staying in the city. You might end up with like 150 people in the city and then 60 people in the country. And then the way that people leave in the percentages, the percentage winds up being the same, where like 3 people leave the city for the country, but then 3 people leave the country for the city. So you kind of hit what you would call like a population equilibrium. If time went on forever, keyword, if it went on forever. So that can't happen. So if you notice, I have this transformation, and I say that the population after k years, which makes sense, would be the transformation or the transition matrix times the population at k minus 1 years, which is the transition matrix times the transition matrix times the population at k minus 2, and so on. So you kind of recursively get back to that it's just going to be t to the k times p naught. And then I have this really nice vector equation to which you look at and go, how in the world did you get from here? Or how in the world did you get to here from here and here? Consider this matrix P and this diagonal, and then here's P inverse. If you go through and do the calculations, you will find that P times D times P inverse does equal that transition matrix. This means that we have a matrix that T that is similar to matrix D. Now the question is, though, that's all great and wonderful. How in the world did you get there? Because just looking at it right now, it just kind of seems like I pulled numbers out of thin air. The thing is, I pulled the correct numbers out of thin air, and I'll show you how I found those numbers. If you were to calculate this, if you were to do some investigation into T, what you would find is that PD is equal to lambda 1 times V1 and lambda 2 times V2, where 1 and 0.93 are the eigenvalues of the matrix T. And this first vector, so 5, 2, is the eigenvector corresponding to lambda equals 1. And then that would mean 1, negative 1 is the eigenvector corresponding to lambda equals 0.93. So what you have, and this is the nice thing, that vector or that matrix that I pulled out of nowhere just simply came from finding the eigenvalues. You probably kind of knew maybe something was going to be related because we are in the eigenvector and eigenvalue chapter, so that was kind of probably a nice little hint there. But the usefulness is I can take the eigenvalues and I can take the eigenvectors and I can just simply diagonalize a matrix just like that. I don't have to guess and check and go, okay, well, what diagonal works and which one doesn't. Now, this is kind of one of those little unstated rules of diagonalization, but because of the way it's defined, it's kind of implied that P inverse exists. So you're not going to run into a case where you find your eigenvectors, you find your eigenvalues, and then all of a sudden you've broken this rule, and now all of a sudden you can't do anything with it because you say, oh, well, I can't find P inverse. These are always going to work. You're always going to have P inverse. So the nice thing is our transition matrix is similar to the diagonal that's made up of its eigenvalues. Lambda 1 and lambda 2. So D is created from eigenvalues along the diagonal. And then P comes from eigenvectors in the same column as their corresponding eigenvalue. So basically all I'm saying is you have to, if lambda 1 goes in your first slot or your 1, 1 slot, then your eigenvector associated with it has to go in the first column. You can't go eigenvalue 1 in 1, 1, eigenvalue 2 in 2, 2, and then switch their eigenvectors. That will not work. So just kind of keep that in mind. You have to be diligent about that. So the diagonalization theorem kind of breaks down into different ways to remember it. So if a matrix is diagonalizable if and only if A has n linearly independent eigenvectors. So there are some, by the terminology, there are some that will not be diagonalizable just because it has dependent eigenvectors. So if A equals PDP inverse, then VI should be independent eigenvectors and the diagonal of D corresponds to those eigenvalues. So a nice thing is if it has n distinct eigenvalues, then it's diagonalizable, which means they're all unique. So that's a way to definitely be able to tell right away that it does work. So, diagonalization of a matrix. Let A have P, or let A to, or A be an n by n matrix with p distinct eigenvalues. Notice this doesn't say there's n distinct. So let D sub k be the dimension of the null space of this. And remember, dimension is just how many vectors are in it. So then A is going to happen where basically the dimension of the null space is going to be less than or equal to the multiplicity of the determinant. Pretty straightforward. A is diagonalizable if the sum of the dimension is equal to n. So basically what that's saying is, do you have still n distinct eigenvectors? That even though the corollary says, the corollary is one of those guarantee theorems, it's a guarantee. It's saying that if they aren't independent, then you have to check. If it has n distinct eigenvalues, congratulations, you know for certain. But then it says if they're not all distinct, then you need to check and make sure there's no dependent eigenvectors. Because basically what this is saying is you can have a distinct number of eigenvalues that's less than or equal to the actual number of columns and rows you have. So maybe it's a 5 by 5 and you only end up with 3, which means it means multitude of things, but like it could mean you have one eigenvalue with a multiplicity of 2, another with a multiplicity of 2, and another with a multiplicity of 1. So then you just have to go through and check, okay, are the eigenvectors still independent? And then the nice thing is, if A is diagonalizable, then the union of all of your bases will be a basis of Rn. So remember, to be a basis, they have to span, which means they have to be independent vectors that will cover all of Rn. So basically there is a non-trivial solution, or the only solution to like Ax equals 0 is the trivial solution, where you get x equals 1 all the way. Or each x sub I is equal to 1, or is equal to 0 the whole way through. Basically no free variables when you try and row reduce it. So now let's actually diagonalize a matrix. So here's our matrix, and it says diagonalize if possible. Now this is going to be kind of the overview because it's a 3 by 3. I'm going to talk through it because you know the processes for finding eigenvectors and finding eigenvalues. So there's 4 steps to implement. First, find the eigenvalues. Always first and foremost, just find the eigenvalues. It'll make your life a lot easier. So if you were to do the determinant for this one, which remember would end up being, we're doing the determinant of, just got to subtract lambda across the diagonal. And then you can do there's many different methods for finding the determinant. You could do a cofactor expansion. You could do our row reduction methods that we talked about. But for this one, what's going to happen is you go through it and you get 0 is equal to negative lambda cubed minus lambda, or 3 lambda squared plus 4. Which you could factor out a negative from that and just get negative lambda cubed minus 3 lambda squared plus 4. Set that equal to 0. Easy to see that if you plug in -1, that would be a root of the equation. Do some long division, and then it will then factor into lambda minus 1 times lambda plus 2 squared with that negative still out front. So this is what I was referring to. So lambda equals 1 with a multiplicity of 1, and it equals -2 with a multiplicity of 2. So we don't know for certain because remember it said that if you had indistinct eigenvalues, then you were guaranteed that it was invertible. Or sorry, diagonalizable. So now we have to check. Key thing, find 3 linearly independent eigenvectors of A. Because if when it comes to finding and working with the eigenvector of A, and we end up that 2 of the eigenvectors are linearly dependent, which remember means one is a linear combination of the other, then we're out of luck and we just say we can't diagonalize it. So it's a 3x3 matrix, so we need 3 vectors. I get ahead of myself sometimes. So remember, so let me see. So it's 1 minus lambda. I have to write it down because I'm going to show you how we would find that particular eigenvector for the first one. 3, 3, 1 minus lambda. All right, so if you were to use the eigenvalue of 1, what you end up with is you get 0, 3, 3, -3, -6, -3, and then 3, 3, 0. And then because you're finding the eigenvector, you set it equal to the 0 vector, because remember, you're trying to find what values make it 0. So what I'm going to do is basically every vector is going to move down 1. And because the third row doesn't have anywhere to go, it's going to loop back up to the top. But I'm going to divide basically every vector by 3. So we get 1, 1, 0. We get 0, 1, 1. And then I'm going to get 1, 2, 1. And then what you'll notice is if I were to multiply, so let's do, if I do row 1 times, or negative row 1, add to row 3, I get 1, 1, 0, and then 0. This row doesn't change. But then I get 0, and I get 1, 1. What that's going to do is that's going to leave me with 1, 1, 0, 0, 0, 1, 1, 0, and then a row of zeros. So I know it's got a free variable solution, but remember, this is just echelon form. Reduced echelon form is everything above and below your pivot is a 0. So if I add negative row 2 to row 1, I get 1, 0, negative 1. I get 0, 1, 1, and then a bunch of zeros. Which means if I were to add x3, remember this is x1, x2, and x3. Make sure that I have enough room to write this. So x1, x2, and x3, which remember this is your x vector. That's going to equal negative x3. Or sorry, that's going to equal positive x3. Because we're going to add it to both sides. And then I'm going to get negative x3, because I have to subtract over x3 from here. And then because x3 is a free variable, x3 equals x3, which is the vector 1, negative 1, and 1 times x3, which, lo and behold, that's the same vector we have there. So that's the process for finding the first. Now the second one, that would just be, you would end up with 2 free variables. And that kind of makes sense. You have a multiplicity of 2, so it makes sense to end up with 2 eigenvectors. Now, keep in mind, it makes sense to get 2 eigenvectors. You then have to check, are they independent? And the answer is yes. I'm never going to get v2 to be equal to v3. Why? Well, look at it. I have a 1 in the second position, and then a 0 for v2, and then a 0 and a 1. Unless I'm multiplying them by 0, there's nothing that's going to work. So, those are independent. Now, the one thing you have to check is, are my 3 vectors linearly independent? So, what you would do is you would set up the matrix, and I would just keep them in the same order. 1, -1, 1, -1, 1, 0, -1, 0, 1. Make that augmented. And then you would find out that that reduces, if you were to go all the way, 1, 0, 0, 0, 0. So only solution to this matrix is multiplying by the 0 vector, so they're independent. Now, remember I said specifically you have to keep your vectors lined up. That is true. They have to line up with the corresponding eigenvector and eigenvalue. So lambda equals 1 needs to go with v1. Lambda equals -2, well, you're going to have 2 rows or 2 columns where -2 is on the diagonal. So if those are switched around, that's okay because they both correspond to the same eigenvalue. You can't just go switching them around with other eigenvalues, that they have to correspond. Remember, so we would have lambda 1 times v1. Now the thing is, we only have a lambda 2 that would be multiplied by v2. Sorry. And then you would get like that. So just keep that in mind. You want to keep those lined up. Now you construct P from the vectors in step 2. The order of the vectors is unimportant, and that kind of gets a little asterisk. The order is unimportant, but still has to line up with, I'm going to say E values just because I can't write it all. So there's our this is our eigenvector matrix. So eigenvector matrix. And then you construct D from the corresponding eigenvalues. Now this is where that kind of the order is unimportant. The order is unimportant until you start pairing up things. Because technically you could have went v2, v1, v3, but you had to make sure that then you would have lambda 2, lambda 1, lambda 3. So to correspond, you would have this. So we said P was one's along the diagonal, a -1 here, -1 here. This was -1. So that would all correspond. And then if you just needed to verify that they were similar, you would just multiply AD, or sorry, a P, because that's the definition, equals PD. And you would find out, yes, they do turn out to be the same thing. Now, again, what you would want to do, though, is you would want to go back, if this was a system that you were running, and you said, okay, I need to find my eigenvalues, and I need to find my eigenvectors, and then put them together. Then, this is something, so like 2x2 and 3x3 are the most I'll expect you to do by hand. But like computers and for like heavy lifting, you could be talking about eigenvalues and eigenvectors that are in like a 100 by 100 system, because you might have all those things that are moving in unison, so you have to be careful there. But again, I'm not expecting you to write down a 100 by 100 matrix and find all the eigenvalues and diagonalize it. But the concept needs to be there, and understanding why diagonalization is important. So, to summarize it, find your eigenvalues, use your characteristic equation, find the eigenvectors for each eigenvalue. If an eigenvalue has multiplicity of k, you need k-independent eigenvectors. So that was why when lambda was equal to -2, you ended up with 2 eigenvectors. Keyword to independent eigenvectors. You couldn't have just said, oh, well, here's like, I think it was like 1, -1, or it was like 1, 1, 0. You can also say, well, here's 2, 2, 2, or 2, 2, 0. Doesn't work like that. You need them to be independent. Find P, that's just line up your eigenvectors. D is place the corresponding eigenvalues on the main diagonal. And that corresponding, again, is the, make sure if the eigenvector that came from lambda 1 is in the first column, make sure that eigenvector 1 is in the first entry for the diagonal. And then celebrate when you verify that it all works, because it can be a lot of work. I'm not going to say much more because this is a long lecture, so that's diagonalization. Practice it. It's just going to be a matter of work hard and make sure. This is just going to reinforce a lot of the eigenvalues and eigenvector stuff that we've done previously.